Welcome to our video on vector spaces, subspaces, linear combinations, and bases. In this video, we'll break down these foundational concepts of linear algebra step by step, making them intuitive and clear. Let's start with the concept of a vector space. A vector space V over a field like the real numbers is a set of objects called vectors, together with two operations, addition and scalar multiplication. These operations must satisfy certain properties, but the most important is that they are closed, meaning when you add vectors or multiply them by scalars, you stay within the same vector space. Let's look at a concrete example. R squared, the set of all ordered pairs of real numbers. We can visualize this as a coordinate plane. For example, the vector 3, 2 represents a point 3 units to the right and 2 units up from the origin. To add vectors in R squared, we add their corresponding components. So 3, 2 plus 1, 4 equals 4, 6. For scalar multiplication, we multiply each component by the scalar. So 2 times 3, 2 equals 6, 4. Both operations produce vectors that are still in R squared, which confirms that R squared is indeed a vector space. Now, let's move on to subspaces. A subspace is a subset of a vector space that is itself a vector space under the same operations. To verify that a subset W is a subspace of vector space V, we need to check three conditions. First, the zero vector must be in W. Second, W must be closed under addition. And third, W must be closed under scalar multiplication. Let's look at an example. In R cubed, consider the xy plane in R cubed, which consists of all points of the form x, y, 0. Let's verify that this is a subspace. First, the zero vector, 0, 0, 0, is in the xy plane. Second, if we add any two vectors in the xy plane, like xy0 plus x2, y2, 0, we get x plus x2, y plus y2, 0, which is still in the xy plane. And third, if we multiply any vector in the xy plane by a scalar, like c times xy0, we get cax cy0, which is still in the xy plane. So the xy plane is indeed a subspace of R cubed. Next, let's discuss linear combinations. A linear combination of vectors v, v2 up to v underscore k is any vector of the form cv plus c2v2 plus c underscore k v underscore k, where c, c2, and so on are scalars, that is, real numbers. Let's see an example. In R squared, if we have the vectors v equals 1, 0, and v2 equals 0, 1, then any point xy in R squared can be written as a linear combination x times v plus y times v2. For instance, the point 3, 2 can be expressed as 3 times 1, 0 plus 2 times 0, 1. This brings us to the concept of span. The span of a set of vectors is the set of all possible linear combinations of those vectors. For example, the span of the vectors 1, 0 and 0, 1 is the entire R squared plane because, as we just saw, any point xy can be written as a linear combination of these two vectors. It's important to note that the span of any set of vectors always forms a subspace. Another example, the span of 1, 0, 0 and 0, 1, 0 in R cubed is the xy plane, which we already verified is a subspace of R cubed. Finally, let's discuss the concept of a basis. A basis of a vector space V is a set of vectors that is both linearly independent and spans the entire space V. Linearly independent means that no vector in the set can be expressed as a linear combination of the others. And spanning means that their linear combinations can produce any vector in the space. In R squared, the standard basis is the set of vectors 1, 0, 0, 1. These vectors are linearly independent because neither can be written as a scalar multiple of the other. And as we've seen, they span R squared because any point xy can be written as x times 1, 0 plus y times 0, 1. When a vector space has a basis with n vectors, we say the space is n-dimensional. So R squared is 2-dimensional, and R cubed is 3-dimensional. Let's put it all together. A vector space is a set with operations of addition and scalar multiplication. A subspace is a subset that is itself a vector space. Linear combinations are formed by adding scaled vectors. The span is the set of all linear combinations of given vectors, and it's always a subspace. And a basis is a minimal set of vectors that spans the entire space, giving us the dimension of the space. These concepts form the foundation of linear algebra and have countless applications in science, engineering, computer graphics, and more. Thank you for watching.